Awesome. I'm going to hide this video panel, and I'm going to hide this panel as well. Great. Okay. Thank you so much for having me here. I'm really excited to be here. This is joint work with Jessica Dye and Paula Gradu, who are both grad students at UC Berkeley. Okay, so before we begin, I always like to tell an audience, even if they're virtual and I can't see them, that I'm a person who stutters. I feel more comfortable saying that. I hope you get more comfortable hearing it. I'm going to skip over all of the proofs. I'm on the faculty job market, and please ask me clarifying questions throughout. So I think Emma's looking at the chat here. Great. So I'll be talking about adaptive sequential experiments, and I'll be working with this simple running example here. So I like going to the gym, and when I'm at the gym, something that I wonder is whether words of encouragement from a coach affect the performance of a beginner athlete. So if I was to design an experiment, here's how I would do that. I would recruit some beginner athletes to come in, and I'd hire a professional coach. And my experiment plan, roughly speaking, would be to give two types of treatments. I either give praise or we just tell them facts about the movement that they'll be doing. And we'll be measuring the outcome, which is the time it takes to run a 100-meter sprint. So the first person comes into the experiment here, and the coach flips a coin and either gives them treatment, which is like the praise, like, you can do it and I believe in you, or the coach gives them the control, which is just a fact, like a standard time for a 100-meter sprint is about 35 seconds. Then the coach pulls out the stopwatch here, and the participant will dash or sprint 100 meters, and will record the time. And the second person comes in, and the same thing happens. The coach will flip a coin, either give the treatment, which is praise, or give the control, which is facts, and measure how long it takes for them to sprint 100 meters. And this happens until everyone's gone through the experiment. And now, with all this experimental data, the coach will estimate what the effect of encouragement is. Now, there's two ways to run this type of experiment. There's a standard experiment where the treatment probabilities are selected before the experiment starts. So imagine I'm going to flip a coin whenever I see someone come in, but that coin, its bias, P, is set ahead of time. And you can also imagine adaptive experiments where the treatment probabilities of assigning, treatment or control are adaptively selected using priorly observed outcomes. So, for example, the coach could look at all the outcomes of the individuals that he's seen so far and use that data to select the next probability of assigning treatment. And the question we're studying in this paper is how or to what extent can an adaptive experiment improve statistical precision for estimating the causal effect. Now, that was a toy example, but there are many other opportunities for running adaptive experiments. So, for instance, certain experiments are already naturally sequential, like in psychology or in human-computer interaction. There's one grad student in a room who has people come in. That's a very naturally sequential thing because you're limited by the resources that you have. There's this proliferation of mobile health devices that can monitor outcomes that are linked to phones and apps where we can send certain types of interventions. And those could be done, you can imagine, in an adaptive way. And finally, A/B testing in online experiments isn't typically done in an adaptive way now, but these experiments are often, the intervention is assigned by a centralized algorithm, and the observations are given to the centralized algorithm as well. So it's possible to do types of adaptive experiments in A/B testing as well. So let me give a historical detour here of adaptive experiments. So one of the earliest papers that poses the question that we're going to be working on is by Herbert Robbins in 1952. It's a very prophetic paper that lists several open problems in sequential design of experiments. So I won't read all the text through here, but let me highlight a few key things that happen. So the first is that Robbins describes Neyman allocation, which is the idea that if we want to minimize the variance of some estimator, the optimal allocation will depend somehow on the outcomes that we're trying to observe. And the question then is how to use or get the optimal allocation. So one idea is a two-stage design, which has been recently studied by these authors here, and I'll get to those in a moment. But this two-stage design works by, in the first stage, you sample, say, outcomes with a probability half, and then at the end of that stage, you use those sampled outcomes to estimate some kind of optimal allocation. And in the second phase, you use that estimated optimal allocation. But then Robbins goes on to consider the idea of a fully adaptive experiment, like the one I described in that first part, where at each time you can use all of the prior observed outcomes to determine the new probability of treatment. And this is listed, sequential designs for adaptive Neyman allocation, that is listed as a major open problem in Robbins' 1952. So that was a while back, and there's been many other types of adaptive experiments. So even earlier than that, Wald was looking at hypothesis testing and proposed the sequential probability ratio test. In the 70s to the 90s, there was lots of work in many different objectives for designing adaptive experiments, like reducing the total sample size or trying to reduce harm subject to meeting some kind of power, and so on and so forth. But these have been critiqued as myopic strategies with adverse effects on power, which are evaluated through numerical simulation rather than strongly developed theory. And that leads to the question, can adaptivity be a harmful thing? And so in 2011, the FDA releases this statement that more or less says you should use adaptive designs cautiously because we don't understand the inferential procedures very well or what the effects on power might be. And as recently as last year, Sai and Rafi have a paper that says small pilots, that is those two-stage designs where the first stage is small, can be misinformative and can often increase the variance relative to non-adaptive counterparts. So I think this highlights there is a need for more principled adaptive designs, and that's what we're going to aim to do a first step towards that at least in this work. So let me now formally state the problem of adaptive Neyman allocation. I'll work in the potential outcomes framework here, and I'll work in the non-adaptive setting first. So there will be T experimental units, like clinical participants in our trial or beginner athletes, and they'll be denoted by an integer little t that ranges from 1 to big T. There will be T binary treatments. They take values in 0, 1, and they're assigned independently with probability P. And that P is a fixed thing the experimenter decides before the experiment is run. And each unit has two potential outcomes, YT1 and YT0. And these outcomes describe what would happen if I were assigned treatment or control. So in our example, YT1 is your sprint time if you were given praise, and YT0 is your sprint time if you were just given the cold hard facts. And these potential outcomes are deterministic. The only randomness in this experiment that I'm assuming in this framework here comes from the randomness in treatment assignment itself. And that means that we're working in what's called design-based inference. Now, the outcomes that we're going to observe, we'll denote them by capital YT, and they are mathematically, as I said beforehand. If you assign treatment, you'll observe YT1. If you assign control, you'll observe YT0. Now, the observed outcomes are random because they depend on treatment assignment, but the potential outcomes are deterministic. And we seek to estimate the average treatment effect. That's the average over all of the units of YT1 contrasted with YT0. So what's the difference in your sprint times? And a very commonly used estimator here is the Horvitz-Thompson estimator, where you average the outcomes, but weighted by the inverse, the probability of assigning that treatment. perhaps with a negative sign if you got the control. And this estimator is an unbiased one, as long as that little p is in the open interval 0, 1. And so before I continue, let me define a few moment analogs here. So S1 is going to be the average over all of the units of the outcomes, the treatment outcomes squared, and take the square root of that whole thing. And S0 will be defined in a similar way, but for outcomes that are control. And these are acting as design-based analogs for the second moment of the treatment and the control outcomes. And similarly, we're going to define this uncentered correlation, also called a cosine similarity, which is the average of the product of the outcomes normalized by the product of the second moments. And by Cauchy-Schwarz, this thing takes values in -1, 1. So how can we design our experiment to reduce the variance? That's the question that we're asking here. So I've written out what the normalized variance is, and you'll see it has two terms. So these first terms here, they depend on two things: the probability the experimenter is going to select and the second moments. So how would I make this term small? Well, if S1 squared was much, much larger than S0 squared, I should try to have that term 1 over p minus 1 to be relatively small to counteract that. And that means that the probability of seeing treatment outcomes should be larger. And likewise, if S0 squared is much larger than S1, that is that the control outcomes have a much higher second moment, then I should make p very small and focus my sampling on those control outcomes there. So that's kind of the intuition of how the experimenter ought to choose p. And there's nothing we can do about the second term here. There's no probability, so we can't really do much with it. And I'm writing the normalized variance, t times the variance here, because I'm emphasizing that the variance will go down at a 1 over t rate, and it's that constant that we're trying to optimize here. So that's really what's at stake in this problem of reducing the variance here. Okay, so the Neyman design is to select the optimal probability p star, which is the inverse of 1 plus the ratio of the second moments there. So that's what the optimal probability is if you work out what the calculus is. And the optimal Neyman variance you would get from using the optimal probability is t times, so this Vn is the Neyman variance here. It is 2 times 1 plus the correlation times the product of the second moments. So what we've done is we've gone from the sum of squares of second moments down to their product. So it's kind of like going from an arithmetic thing to a geometric thing. So that's the improvement that this design offers. But the catch is that it's infeasible to run. Why? It requires knowing what those second moments are. And if you knew all the outcomes, great. You could compute the second moments and you could run this design. You'd have very good variance. But the problem is that the experimenter may not know, and typically doesn't know, all its outcomes in advance of running the experiment. So the question we're asking is whether we can provably attain the Neyman variance in an adaptive experiment. So a little bit of prior work. There's two main papers to compare to here. They both have that two-phase experimental design, which we also call explore and then commit. So Han et al. In 2011 worked in an IID superpopulation assumption and was motivated by semi-parametric theory, but a lot of what the problem statement comes down to is very similar. So they get within a constant factor of the Neyman variance, but they're not showing they can achieve it. They're focused more on inferential procedures. And finally, Blackwell last year et al. Have this design-based framework that we have. They propose a two-phase experimental design, but there's no theoretical analysis of the variance there. It's mostly to be to highlight to practitioners what good design choices are. Okay, in this paper, we're going to construct an experimental design whose variance provably converges to the Neyman variance, and we're going to develop inferential methods. Great, so our design is called Clip-OGD, and let me discuss that more. So we're in the adaptive setting now, And what that means, we're still estimating the average treatment effect, but we're going to have this adaptive protocol where for each unit, we're going to assign treatment ZT equals 1 with probability PT or 0 with probability 1 minus PT and observe what the outcome is. What's different now is that these probabilities PT can be random and they can depend on the previously observed assignments and outcomes. So rather than the Horvitz-Thompson estimator, which isn't feasible to use here, we're going to use the adaptive Horvitz-Thompson estimator because we get to observe these conditional probabilities, and so that's what we'll reweight by. This estimator is, again, unbiased so long as these conditional probabilities are in the open interval with probability 1. So let's see what its variance is. It has a similar form as the variance did last time. There are two main terms. So this first term involves the outcomes and the probabilities. So we can hope to make this term small by selecting the probabilities in a good way. This other term, nothing we can do about it. It's just the way it is. So how do we make this second term small? What's the idea here? Well, if yt1 squared was much larger than yt0, I would like to make PT larger, closer to 1. So it's a similar kind of intuition as it was last time, but there's a catch now. And that is, in particular, I'm only going to observe yt1 or yt0. I'll never observe both. And moreover, I have to pick the probability PT before even seeing yt1 or yt0. So how small can we make this first term if we only adaptively and partially observe the outcomes? So the first key insight of our paper is that the Neyman design is like the best fixed design where these random probabilities are set to be just some fixed P. And comparing to the best fixed design is actually a regret minimization problem. So let's see that more formally. And I want to remind you of this term here. We're going to see it in the next slide. So for each function t, or each experimental unit t, I'll define this cost function that maps probabilities to the reals, and it's defined as follows here. And the intuition is that this is the part of the variance that the experiment, that the subject t contributes to, that we can control through our choice of the probability p. And the name and regret of an adaptive experimental design will be denoted R of t, and it's going to be the difference between the costs that you incur with the probabilities that you adaptively play, contrasted with what the optimal fixed probability P would be. And that optimal P, when I say optimal, it gets to know all of those cost functions, and in particular, it gets to know what all the outcomes are. And how does this name and regret relate to our goal of getting the variance small? Well, the normalized variance, when I subtract off the normalized Neyman variance, that additive difference is just 1 over t times the expected Neyman regret. And so in particular, making this additive error small, so converging to the Neyman variance, is equivalent to getting sublinear Neyman regret here in expectation. So I kind of think about this as being an inherently computational problem, because we're going to have to use some kind of algorithmic techniques to make this regret be small. Great. So these functions are convex. And so to convince you of that, I put 2 of the functions here. So this is an instance of online convex optimization. So we can use insights from that literature there. 2 catches. It'll be different from cumulative regret, things that UCB and X3 are designed for, where you seek to play some good actions. There, the functions are linear. Here, we're having a different kind of problem. We're making the variance of some estimated difference in the means to be small. There's also a technical issue that I'll describe more in a little bit, which is that the FTs have unbounded derivative near the boundary, so we need new algorithmic techniques. So the first thing you could try is online gradient descent, and it works in the following way. You pick a probability, let's say 1/2. You see some cost function here. You incur that cost. You get the gradient, you go a little bit in the negative gradient direction, and that probability is what you play at the next round. and we see some cost function. We incur that cost, look at the gradient, go a little bit in the negative direction of the gradient, and that's the probability that I'll play in that third round, and so on and so forth. And typically, if you set the parameters right, OGD achieves square root t regret under some assumptions. And the big catch here is that those assumptions aren't going to be satisfied, but we can still try to make use of the online gradient descent principle. So what's going to go wrong? Well, first thing that's going to go wrong is gradient axis. So in particular, my cost functions depend on both of these outcomes, and only one of them is going to be revealed. And likewise, its gradients depend on both these outcomes, and only one of them is revealed. So getting around this is not too bad. We can construct stochastic gradient estimates using the Hurwitz-Thompson principle here. What the real problem is that this cost function is unbounded. So what can go wrong? Well, if I play some probability, which is well in the interior of this interval, then I know that the cost is not going to be too large. But if by accident I get too close to the boundary, then I'm going to blow up, and that cost can become very, very large. And if I do this wrong even one time, I could have a Neyman regret, which is super linear and prevents me converging to the Neyman variance. At the same time, we do want to allow ourselves to get close to the boundary. Why? Because the optimal P might be close to there. So I have to, in a very controlled way, allow myself to get close to the boundary, and online gradient descent will not do that by itself. So what do? We propose this solution, which is probability clipping. So you're going to have this clipping interval at time t, and if gradient descent gave you some point here, we're just going to clip. We're going to project that probability back into this interval here. And so this will prevent us at time t from getting too close to the boundary. But as I said, we need to allow ourselves to get closer to the boundary, at least over time. And so what the idea is this clipping interval will grow over the many iterations here. So as the iterations go on, this interval will get larger and larger until it gets very, very close to this boundary here. And we call this idea, this algorithm, Clip-OGD. Clip for this clipping step, OGD for online gradient descent. So here's the algorithm in pseudocode. I just want to point out a few things. There's two input parameters here. So the step size, how far do you move when you do a gradient step, and the decay parameter alpha, which controls how fast we'll grow that interval there. So we are indeed going to clip in this range delta t to 1 minus delta t, and that delta is initially half, so that range is right at a half, but will slowly grow over the iterations, and the rate at which we grow depends on this alpha, which is the decay parameter. And we're going to estimate our gradients with the Hurwitz-Thompson estimator. And so here's what our analysis is. Let me first begin by giving the conditions under which we're going to work. We assume that the second moments are bounded from below by a constant. This prevents the outcomes from like going to 0 really fast and making the problem a degenerate one. And we also are going to need that the fourth moments are bounded above. This is the more substantive assumption, I would say. And we also need the cosine similarity is bounded away from -1 by a constant. So these types of assumptions are very common in design-based inference. Again, this is the fourth moment is the substantive one, and the other two are relatively mild. What I want to focus on is that there's no moment. Sorry, these are moment conditions, and there's no ordering assumption here. So you can have drift or non-stationarity in your outcomes if you would like. And we show that by setting the step size to 1 over square root t and this decay parameter to square root 5 log t, Clip-OGD guarantees that the expected regret is sublinear, and in particular, it's going to be order square root t. And I'm hiding some sub-polynomial factors when I say this. So this is the first experimental design, which I think provably attains the Neyman variance in large sample sizes here. So a few more things in the time that I have left. We also develop a rigorous theory for asymptotically valid confidence intervals. And we construct the way we do this is we construct a variance estimator that will be conservative for what the true variance is. That conservativeness is always necessary in design-based in inference. I'm happy to talk more about it in the Q&A. And we show that using Chebyshev bounds, you can cover at the nominal rates. That can be improved if we had essential limit theorem, which we're currently working on. So I'm kind of out of time here, but let me briefly say that we have some simulation results from a microfinance experiment of Grow and McKinsey in 2016. Let me show you a few things. On the y-axis is the normalized variance. On the x-axis is the number of rounds in the experiment, or sorry, the number of units that we see. So Clip-OGD does converge to the Neyman variance, which is in red. Bernoulli is in black if you just set p to be a half. Explore then commit, this two-phase design does not converge to the Neyman variance. One thing I have to point out is that Clip-OGD incurs this adaptivity overhead. So if your sample size is small, you could achieve a higher variance here, but that can be partially mitigated through choosing a better step size, which we do in the appendix of the paper. I'm happy to talk about that. And it turns out that if you swap the first 100 potential outcomes, you can get the two-phase to perform worse than Bernoulli, but Clip-OGD remains unaffected. Great. So in summary, we show the problem of adaptive Neyman allocation is equivalent to an adversarial online convex optimization problem. And using that insight, we develop an experimental design that achieves square root t Neyman regret and thereby achieves the Neyman variance in large samples. We provide necessary tools for developing valid confidence intervals, and we have a lot of other additional exciting results, like comparing other designs and other objectives in the paper. And there's lots of future work, like what's the min-max rates of Neyman regret? Can we drive a central limit theorem? And can other adaptive design problems be approached in a similar way? That's all I have. Thank you so much. And I'm happy to answer any questions that you may have. Thanks.
Thanks, Chris. Great talk. So there's one question in the Q&A, and then I think Ying has some questions to ask you. So I'll start with the Q&A one first, because it might be shorter.
Great.
So the question in the Q&A is it possible that the moments do not exist, and what to do here? I think this was on the slide where you were talking about the little c and the big C.
Oh, yeah. So here in design-based inference, these moments are always going to like exist simply because we're just summing up t things here. So these moments are always going to exist. That's totally fine. What could go wrong is that the fourth moment becomes very, very large. So imagine if your experiment's getting bigger, people can suddenly sprint 100 meters much faster, or it takes a lot longer for them to sprint. That's the kind of worry that we're going to have. So the moments are always fine. Like the existence is not the issue here.
Great. Then I'll let Ying take over with some questions.
Okay.
If you
Sure. Thank you, Emma. Yeah, so I have two quick questions. The first one is, what about the sampling-based settings, like the outcomes or ID from a population? I can imagine in that case, you can estimate more things.
Yeah. So there's a lot of opportunities there. So the first, so I should say that I've pointed recently to a paper which came out about the same time that studies that. So it's Jinglong over in Boston. So I highly recommend reading that. I need to read it in more detail. But there's a few things that a sampling-based perspective would give you. First off, if they're IID, there's no like drift. And so that might be helpful in designing algorithms that don't have to protect against that sort of worst case. You can also, I think, we are going to estimate the gradient of these like adversarial functions one at a time. But if you were in an IID setting, there's really only one function that you can get stochastic estimates of the gradient at each step. So you can use a lot more of the data there. So that'd probably improve some of the rates here as well. So I think square root t is probably not the best thing you can do in a sampling-based perspective.
Got it. Thank you. The second question is, like with adaptivity, I think not all designs can lead to valid inference. So probably when comparing like the regrets, you don't want to take account for those designs that don't lead to inference. But I don't know how you can concretely do this, but just a high level like idea about it.
Yeah. So you're totally right that just getting this name and regret to be small alone doesn't guarantee valid inference. So like I don't know of another notion of regret that would like guarantee that. So you could optimize both things at the same time. But we can show for this design that valid inference is possible here, and I'd be happy to talk about the details of how that variance estimator works and so on and so forth. But my sense overall basically is that if you can get this to be sublinear, and you can also show that your probabilities aren't like, going to 0, 1 super fast, that they're mostly inside that interior, then you should be able to do inference there. And this is very different from adaptive designs that are run, let's say, like with a bandit algorithm. So there you're trying to optimize something else, and that is cumulative regret. There it's a lot trickier, just because you solve the problem, or things that solve the problem well may not have valid inferential procedures.
Great. Thank you for the great discussion. I think it's a good time to wrap up. So let me share the screen again. Oh, Chris, can you stop sharing?
Yeah, I gotta figure out how to do that.
Okay, I just started. I think.
Okay.
Yes.
Great. Thank you.
So thank you, Michael and Chris, for the great talks. Next week, we'll have Richard Gore from University of Cambridge. He'll talk about confounded selection via iterative graph expansion. We hope to see you next time. Thank you. I'll stop my sharing and stop recording.